Hi, everybody. Welcome to another episode of Building Science Digest. I'm your host, Christian Kennedy. Today, I have the pleasure of speaking with Galen Burrell, who is a senior building science strategist. I want to make sure I got that right there.
Got it.
Galen, welcome to Building Science Digest.
Good to see you, Christian.
Good to see you. We are going to talk about heat in the built environment today. Galen has been with Saint-Gobain North America for over a year and a half now. And before that, you were basically an architectural design engineer. I'm butchering that?
That's pretty much right. I
Sort
actually
of,
spent the
okay.
first 20 years of my career as an architectural engineer and actually focused on as a lighting designer.
Yeah, there it is.
And you
Yep.
could ask, like, what connects the dots between a lighting designer and building science, and in this case, heat.
Heat does, yeah.
And there's actually, you can think of light as being the other side of the coin is heat.
Sure.
Because light and heat kind of go together.
Yeah.
Your eyes receive the light and your body feels the heat, but they're actually kind of one and the same.
But they're one and the same. Okay, interesting. Yeah. Give us an idea of why this really matters, and I believe there's three, so we can dive into each of those. But why does it matter? Why is heat so important to us as occupants, and then to you as this is your industry?
So let's go through those. So the first one is energy and carbon. Right?
Yeah, right.
And so heating and cooling represent 40% of our of the energy consumption in commercial buildings today. And on the residential side, it's closer to 50%. So these are probably the single largest consumers of energy, whether you're talking commercial or residential buildings. So it's an obvious place to be focusing our energy and how do we reduce those numbers if we're trying to lower our carbon footprint in this country. If you think about how is that possible, like 50% is a big number on the residential side.
Huge, yeah.
It's like, and there's a lot of other things. There's lights, there's appliances, there's all sorts of stuff. We're charging electric cars now. Why is heat such a big issue? If you double click on that, in the northern half of the country, which is our kind of cold climate zones, that represents about 37% of our existing building stock. Of those homes, of those 37% of the existing homes, half of them are currently uninsulated. They have no insulation in their walls.
37% of homes that are in the northern climate, half of those 37% aren't insulated, is what you're saying.
Yeah, none whatsoever.
That can't be comfortable.
It's no, they leak like a sieve, right? So there's basically no resistance to heat transfer. So if it's 0 degrees outside and you're trying to keep your home to 70 degrees on the inside, there's not a whole lot in between those walls that's going to keep that heat just flowing to the outside.
That's incredible. So it's any type of heating or cooling, right, for that matter as well, or is it just heating?
Correct. That works to the other direction. The southern climates where it's hot, if it's really hot outside and you're trying to keep it cooler inside, the same will happen in reverse. So we have a huge. On one hand, it's a huge problem. On the other hand, it's a huge opportunity. There's a huge, opportunity for us to address both the carbon footprint of our existing building stock, but also to save homeowners money on their energy bills.
Yeah, it's costly. Right?
Oh, absolutely.
It has to be expensive to the homeowners or the building owners. So that's two. So we've touched on energy, carbon, and then comfort. So what is that third one?
Yeah. So, and actually energy and carbon, I kind of grouped together because they're kind of two sides of the same coin. But yeah, the second one being comfort. The whole purpose of a building is to create shelter for humans. We should expect more from those shelters. Right. If you think back, thousands of years ago, we thought a shelter was a cave or, going under a tree to seek shade from the sun or, get out of the rain or what have you. We've come some ways. Yeah. We've come some distance since the few thousand years ago in terms of civilization. And so we should expect more from our shelters now.
Agreed,
and indeed, real estate are the biggest investment that we make for most people.
Yeah, certainly.
And so, of course, we should expect to have, excellent comfort inside those homes that we spend so much of our time in and so much of our resources on.
And one way to achieve that is through that insulation that we kind of were discussing just a minute ago.
Yeah, insulation is one of those. We'll get into solutions, more I think throughout the episode. But yeah, there's a lot of things we can do to make our homes more comfortable and more energy efficient. So those are the two.
Those are the big two.
I think the third one would be, in my mind, it's something that's talked about a lot in the news right now is resilience. It can mean a few different things, but in this context, how I'm referring to it is resistance to changing weather, more extreme weather. We've all, felt the increasing frequency of heat waves. We can talk about some examples later on. More extreme heat, more extreme cold, and how do we make our buildings more resilient to that changing weather, that more extreme weather, and And coupled to that is how do you make them more resilient to that extreme weather, which sometimes come at the same time as power outages.
Ah, okay.
Right? When you have the extreme heat, sometimes the grid can't keep up, the grid shuts down, and all of a sudden you have hot weather and you have no power. What are you going to do?
That's not good.
How can our buildings be more resilient to those circumstances? So that's kind of the resilient topic.
Interesting. Okay, so those are the 3, 4: energy, carbon, comfort, and resilience, or the big 3, 4.
Those are the big 3. I mean, there's other smaller ones, but I think for the purpose of this conversation,
we'll stick with
we
those.
can cover a lot of ground with those 3 topics. Yeah.
So on those topics, within each of those, and we can start with energy and carbon, what does that look like from an industry standpoint? How is it changing? How is it evolving? What are we doing? What are you doing to make that better, to increase the energy efficiency and to decrease kind of the carbon footprint?
Yeah, so on that side, it's really driven by the energy codes on both the commercial and the residential side. So increasingly, the energy codes are requiring more insulation, more air tightness to reduce infiltration of warm or cold air into the building.
Oh, yeah.
And so on new construction, we tend to be following where the codes are pushing us, and they're pushing us in that direction to try to reduce energy consumption in our buildings through improving the envelope. That side is really driven for the most part by energy codes and also by the private sector as well. On the commercial side, you have companies like the Googles of the world, the Amazons of the world. They're forming their own climate targets that are kind of mandating the energy performance of their buildings to be much more energy efficient.
Oh, like self-mandating, self-policing almost?
Exactly.
Oh, interesting.
Yeah.
Okay.
So because they see it as affecting their bottom line, so they're kind of taking it upon themselves to increase the efficiency of their existing building stock and their new building stock.
That covers energy and carbon, right? If we wanted to dive deeper into, say, resiliency or comfort, what do those 2 topics look like? On a deep dive into comfort, what is happening or what is powering or pushing that?
Yeah, so comfort, there's kind of 3 things that how we should break that down. There is what are the factors that cause comfort, and then what are the ways that we can measure it. You can't change what you don't measure, right? Yeah. And so we have to know how to measure it, and that's both in the design side and also once the building is occupied, how can we measure comfort? And then, of course, it's what can you do about it?
Sure.
So then we can get into some solutions. So what are the factors that influence comfort?
Yeah.
I would say there's 4 physical factors that influence comfort. All of these will be familiar to everybody. And then there's 2 physiological factors. So the 4, I'll call them physical factors, are air temperature.
Yep.
That's just,
you can name that one, yeah.
Yep, you know that one.
That's
you
a good one,
you have a thermometer on your watch, probably in your car, in your house. And then more nuanced to that is the radiant temperature. Sure. So that's the temperature you feel if you're sitting in the sun or you're sitting in the shade, and that difference that you feel. So an example would be, when you're outside and you walk out on maybe a cool sunny day and you're in the shade, you feel kind of cold, right?
Yeah, absolutely.
And then you go out in the full sun and all of a sudden you feel totally warmer.
Right.
No better place to exemplify this than where I live in Colorado.
Oh, gosh, yeah.
Where it's one of the sunniest places in the country. We have very cold winters. Yeah. It can be 30 degrees outside, air temperature.
Yeah.
You go outside and it's sunny, you can go down to a t-shirt because it's so warm in the sun.
Wow.
So that's the effect that radiant temperature has.
Okay.
And we actually have the same thing in buildings, right? If you're inside a building and you're far away from the window, you might feel one thing, and then you go closer to a window where the sun is coming in, you feel a lot warmer. That's the radiant effect.
Oh, absolutely. Yeah. I mean, we experience that, I think, here in the Malvern office. Right?
Exactly.
Yeah, absolutely.
Yep. And then there's humidity.
Okay.
Right. So the more humid the air is, typically the more you'll feel that heat. So if it's hot and humid, that tends to be more uncomfortable than
it's uncomfortable
than hot and dry, for example. Or so humidity has a big influence on comfort.
And you can control that inside, right, through some of the works that you're doing, and then again we'll touch on that later. But just to be able to control the temperature, whether it's the radiant or the air temp or even the humidity inside a commercial or residential structure, I think is so fascinating.
For relative humidity, oftentimes that's mostly controlled through the mechanical systems to humidify or dehumidify a space. It's more of the temperature aspects or more can be controlled through the more passive measures that I think we'll talk about on the envelope. Yeah,
absolutely.
And then the fourth one would be air speed. So again, we've all had this experience where you turn on a fan, you feel that breeze blowing across you, you feel instantly cooler. That's why we use fans in the summertime. It's also why you feel cold in the winter if you're sitting next to like a drafty window, right? You have that air kind of blowing across your skin. You feel a little bit cooler.
I can picture all of those. I've certainly been in a situation where I've experienced all those to the worst of it as well.
Totally. Yeah, these are all very relatable.
Yeah,
this is not rocket science here. So those are the 4 physical factors.
Right, and then you said
comfort.
There's 2.
And the 2 other, like I'll call them physiological factors, are your metabolic rate.
Sure.
So think about like maybe after or before lunch you go and you work out at the gym or something, right? And you kind of get worked up, and then you go sit down at your desk and start working again. You're still kind of hot. That's when your metabolic rate is higher because you've just done a workout.
Interesting.
And some people just have naturally higher metabolic rates, and some people have naturally slower ones. In other words, some people just create more heat, and some people create less heat.
Gotcha.
And that'll definitely affect your comfort because you're just generating more or less heat yourself within your own body. And so that's very individual. The other one is just your clothing level.
Oh, okay. Yeah, absolutely.
And that's actually more of a cultural one, right? So you go to some cultures and everyone shows up to work in a full suit and tie, jacket, everything. And so they can probably be a little bit cool. The temperature can be a little bit cooler in the office and they can still be warm.
Right.
Whereas you go to some places, where people show up to work in a t-shirt, they're going to have a different perception of comfort, higher, depending on the temperature. So
interesting.
Yeah, those are the kind of 6 factors that relate to comfort. And the tragedy is most people only think about the air temperature.
I was just going to say, I think the biggest one is just, how warm or how cold is it in the room, right? In whatever room they're in. And either at home or at the office, those are certainly that is certainly the first one that I think of.
Typically, the HVAC system only thinks about the air temperature too. That's kind of that's kind of the surprising thing. The system that's in your building designed to keep people comfortable is typically only looking at just one metric,
air temp.
Yeah, it has a thermostat in the room, and it's using that as its and maybe a humidity sensor to control the humidity, and it's using that as a proxy to gauge how much to condition the space. When in reality, it can be very different across. Like an office floor plan, for example. Yeah. So let me give you a fictitious example.
Let's do it.
So let's say here in our office, right, we have an open floor plan.
Yep.
If you're someone that sits in the middle of the office, maybe near the copy room or something, you're kind of far away from the windows. You're gonna have one experience, right? Let's call that person Jenny. Jenny's sitting near the copy room, away from the windows. She has one experience. Then let's come up with someone else named Wesley. Okay.
Great names.
Yeah, and he's sitting next to a west-facing window.
Wesley there you go.
Is facing west, and so he's sitting next to the windows. And let's say it's the afternoon, right? And the entire office is conditioned to 72 degrees. Let's think about what happens over the course of the day. In the morning, they might be feeling the exact same temperature. 72 degrees. Now in the afternoon, as the sun starts coming around to the west side of the building, what's going to start to happen?
Well, Wesley's going to start getting a little warmer. Right.
Well, and why is that, right?
Well, let's see. The sun is going on that side. It's radiant heat, radiant temperature, right? Coming through the glass.
Yeah, the sun. Yeah, the sun's coming in.
Yeah.
It's coming in through the windows.
Yep.
So first, that sun is hitting the glass.
Okay.
And the glass starts to heat up, and Wesley starts to feel a little bit of warmth from that glass. Not too bad. Maybe unbuttons his jacket. Yeah. Still good. Then later in the afternoon, the sun's coming a little bit deeper, and pretty soon Wesley is completely enveloped in the radiant energy of the sun. But at that point, Wesley's not feeling so glorious anymore.
I was going to say, he's probably been in the sun all day, more or less, yeah.
And so at that point, Wesley has a completely different perception of comfort than Jenny does in the middle of the floor plan. Even though the air temperature still says the exact same thing, 72 degrees, Wesley feels hot, Jenny feels cold. And now you can imagine a few other variations of that. Maybe Jenny's sitting underneath the diffuser, and so that she has like cold air blowing directly on her. And maybe Wesley also worked out at the gym right before and has that going. So there's all these different variations where different people, based on their different metabolic rates, where they're sitting on the floor plan, will have completely different comfort perceptions. But according to the HVAC system, it's doing its job.
Right, it's 72.
72 degrees.
That's it, yep.
Yeah. So that's, to me, that is that kind of illustrates the nuances in how we measure comfort, some of the challenges or shortcomings with how we measure it, and starts to suggest some of the solutions that we might use to address it.
Let's dive into those. I mean, what are some of those solutions? I know, and there we've just kind of focused on 6 factors that can go into someone's comfortability.
Some would suggest that you actually want to allow for that variation.
Oh,
so some variation across the floor is actually okay, as long as you allow people to adjust their seating arrangements based on their preferences.
Okay.
So if you're someone that likes to be warmer, maybe you should be allowed to sit near the window where it's going to get naturally warmer, right? And allow people that are just naturally too hot and
that want to be cooler.
Yeah, then let them sit somewhere else on the floor where it tends to be cooler. So before we even get to solutions or building solutions, we can think about something like that, where you just give people more flexibility to sit in different places that are more amenable to their own preferences. The other thing is just recognizing that everyone has their own personal comfort, and there's solutions out there that provide comfort local to where the person actually sits.
Okay.
So again, we're not getting to the building solutions yet. This is just local comfort solutions. So for example, at home, at my home office, I'm always cold. I don't want to heat my entire house to 72 degrees while I'm the only one home.
Right.
And so I have a radiant foot pad that keeps me warm. You put your feet on that thing and it just keeps you warm.
Oh my gosh.
There's
perfect.
Radiant blankets you can put on. Like people do all sorts of things, and you can do that in your office too, just to keep yourself a little bit warmer.
Your personal comfort.
Yeah. Or you can put a little desk fan on your desk to have a little breeze on you. So there's some local comfort things that you can do. On the building side, if you're designing a new building from the ground up, you can be more thoughtful about how to address those things. And that's where really it comes down to improving the building envelope is really where it needs to start. So that's things like adding more insulation in the walls, because the more you insulate the walls, you keep the walls a more constant temperature. They're not, if it's 0 degrees outside, the walls aren't becoming, 0 degrees or 20 degrees, which will radiate cold temperature towards your skin. And so insulating the walls is really helpful. Highly insulated windows. It really all comes down to insulation.
Okay.
And then coupled with that, air sealing the building so you don't have those drafts coming in. Especially on the commercial side, the windows are a big deal as well.
Yeah.
We use that example with Wesley and the west-facing windows.
Yes, Wesley facing west.
Yeah. So there is something that can be done about that as well, right? You can high-performance windows. They're getting better and better every year. On the static side of things, there's high-performance coatings like low emissivity coatings that limit the amount of heat that comes through the windows while still emitting a lot of light. Or even better, there's things like electrochromic coatings. You mentioned the sage glass window.
Right.
That's an example of electrochromic that it changes their tint depending on whether the sun is on the glass or not to allow more or less heat through the windows.
So impressive.
It's really cool technology.
Really cool, yeah.
And so those are that's a really good example of innovative technology that can control heat while still giving people, a connection to the outside.
Sure.
And that's the amazing thing I think about windows is that that's like a transparent part of the envelope that connects people to the outside, but still is serving this important function of, insulating at the same time.
It connects them to the outside, but it protects them from the outside.
There you go.
Right? Is
exactly.
that a slogan? You just come up with a slogan?
I think you're onto something there.
That's amazing. So that focuses on the building envelope and is that the resilience then there, or is that the energy efficiency part of what we're discussing here today?
It's actually a bit of both, right? If you think about it, the same things that promote comfort in a building, a better insulated envelope, an airtight envelope that limits infiltration, those are the same things that promote energy efficiency by limiting that heat transfer, so you're not heating or air conditioning your building and just letting it go right outside. And those are the same things that promote resiliency.
Now, do those factors play similar roles when discussing residential and commercial? What is the difference really between residential and commercial?
To me, one of the main differences is kind of like the occupancy type and the use of the building. So commercial buildings are almost always internally load driven. Let's take an office building. It's computers, it's lights, a lot of people in there generating heat and humidity. And so almost all the time those buildings are in cooling mode.
Okay.
Even in the wintertime, this building that we're in today is probably in air conditioning mode because there's so many internal loads. Maybe in the mornings, it has to do a little bit of
warm up overnight,
of morning warm up, but for the most part, commercial buildings are often cooling dominated because there's so many internal loads. So then think about a hospital, like it's even more so. There's like so much equipment and stuff generating heat. And so for commercial buildings, no matter where you are in the climate zones, oftentimes it's more trying to cool the buildings rather than heating the buildings.
Regardless of climate zones?
Almost, yeah. Wow. And again, that's not a universal.
There's some outliers.
There's some outliers, sure. And mornings and the coldest days of winter. Maybe there's definitely some heating going on there. And so as a result, commercial buildings tend to be in heat rejection mode. They want to keep the heat out. The windows are always designed to reject heat. They want to bring in light, but they want to reject heat. The roofs, you want those roofs to be as light as possible, cool roofs, right? And California requires this.
Yeah.
I bet it's not long before more states start requiring that.
Trickle down effect. Sure.
Oftentimes California is the first to do those things. But yeah, cool roofs. It can keep in a house a cool reflective roof can keep a home a few degrees cooler in the summertime. Typically, commercial buildings are designed to reject heat, whereas on the residential side, it's a little bit more nuanced because it's much more climate dependent. And oftentimes in a home, you actually want to let that heat in.
Right.
I imagine here in Pennsylvania, and certainly where I live in Colorado, in the wintertime, you kind of want to have that heat come in through the window, right?
Yeah.
That's probably where you.
I look forward to seeing the sun come through the windows and warm up the inside.
Exactly. Sure. If you have a pet like a dog or a cat, that's probably where they gravitate.
The sun spot. I know every pet that goes to the sun spot.
Exactly. Yeah. They gravitate towards the sunny window and they lie down, curl up there. And it's for good reason. It's like that feels good to be in that heat, in that heat in the wintertime. On the residential side, it's a little bit more seasonal.
Okay.
So in the summer, of course, you typically want to reject that heat through shading. But in the wintertime, in a lot of climates, specifically those northern climates, you actually want to bring that heat in.
It's more than welcome.
Yeah.
More than welcome
It makes it a beautiful space. And so things like windows are a little bit different. They're designed to usually emit more heat than commercial windows are, and then you shade them such that the shading devices will block the sunlight in the summer, but at the lower sun angles, it'll let it in through the window, so you can harvest that heat.
Okay.
So that's kind of the main difference, I would say, between commercial and residential is kind of that seasonality aspect and also the use of those buildings, more of a heat rejection mode in commercial and more of a,
neutral
or balanced approach with residential, specifically in those temperate climates.
Yeah, and based off of the occupancy. Do we want to dive into the solutions now? And because I think what we've discussed before is that the solutions are set and are eerily similar across each of those factors, but they serve or conduct different purposes.
Yeah, I mean, because we talked about resiliency as well, and those same solutions, adding more insulation, air tightness, those are the same things that help resiliency too.
Oh, okay.
If you think about, a heat wave, what do you want in a building when you have a heat wave?
Cool air.
Yeah. Well, hopefully you have cool air coming in to relieve that. And hopefully your power is still on in your home, or your office building or whatever, so that you can deliver that cold air. But sometimes actually that doesn't happen, and there are some worst case scenarios. And a couple examples would be, in 2001, we had the Northwest, in Oregon and Washington and British Columbia. They went through a record heat wave. British Columbia had 115 degree temperatures, the highest temperature ever recorded in all of Canada happened up there. British Columbia. This is not the South. This is British Columbia. And Portland, Oregon was 110 degrees or something. It's crazy temperatures. And at the same time, because there's so many people turning on their air conditioners, people were rushing out to the store to buy air conditioners for their homes.
Oh my goodness.
The grid was getting overloaded. So they were having rolling blackouts because the grid couldn't keep up with all the demand. So they're having these record high temperatures and power going off.
And they're having rolling blackouts.
Yeah, it was a bad situation. So I think, unfortunately, 1,400 people died up there in that heat wave due to heat related
incidents,
causes. So that is kind of the worst case scenario. So sometimes it's not as simple as just turning up the air conditioner.
Right.
That just further reinforces why you need to have passive measures in place to accommodate that those types of extreme temperatures. We call it There's the resilience, then we call it passive survivability.
Oh, interesting. Okay,
that's
a term I haven't heard yet.
Yeah, you think about what that term means, right? So passive survivability. What happens if you lose power, and so you can't power your active systems, your air conditioner, your heater, your lights, your water sometimes. This also relates to water. Can you survive in your home when all that stuff goes off and you're in like the extreme temperature? And so actually LEED has a credit in its rating system now that addresses this, and the credit is relating to, can you maintain comfortable temperatures in your building even if the power goes off for 4 days straight and and the outside temperature is at like the maximum, basically.
Wow.
Or the maximum hot or the maximum cold. It works both ways. And so how do you do that? It's through the envelope of your building. That's the only way to really address that.
This is so interesting.
Highly insulated building, so maximize the insulation in your walls, your windows, your roof, your foundation, to minimize the heat transfer through your envelope, and then also the air tightness, right, to minimize the infiltration through the envelope. That's how you address both the comfort, the energy savings, and make your spaces more
passive survivability.
Yeah.
Interesting. Okay. When I sat down with Stan Gatlin, we talked about indoor air comfort and air tightness, and he mentioned it's incredibly important to have that. It's interesting how, although we're talking about heat here today, you've mentioned some other topics, and it does feel as though it all connects.
It all happens at the envelope. I mean, that's where building scientists spend all of their time, pretty much, is at the building envelope.
And and you're not really focused on specific products. It's more systems, right? And how can everything work together?
Exactly. Yeah, it's all a system. And you mentioned Stan with the air episode, and I think Lucas was talking about moisture.
Yeah.
All those things relate to heat as well.
Yeah.
Because if you make an airtight envelope, which I'm sure Stan talked about, right? You want to limit that air infiltration in the building. Of course, that has effects for indoor air quality and comfort and so forth. But also, it's coupled with heat as well. Because if you think about introducing, cold, humid air into your wall, what's going to happen? Like when it hits a cold surface, it's going to condense, and then all of a sudden you have moisture in the building. That's probably what Lucas was talking about. What happens when you get moisture trapped in your wall? Not good.
That's the worst. That's the worst thing that can happen.
That's the worst thing that can happen.
Now, moving forward, for heat in the built environment, are you anticipating more changes, code changes, or just trends that incorporate strictly what we're talking about kind of here today?
Oh, yeah, definitely. The codes will always be changing. They have their cycle that they go on, and they're constantly making those more stringent with respect to the energy code. Continuous insulation is one example, right? It used to be that people would only use, cavity insulation to satisfy the insulation requirements. Right. And then increasingly the code started requiring the use of exterior insulation in addition to the cavity insulation. That is just only going to continue. It's happening on the commercial side. It's happening on the residential side. The air tightness requirements are continuing to become more rigorous. I think the other thing that's interesting is, in some ways, the climate, the weather is changing almost faster than our codes can keep up with.
Yeah, certainly.
And so I think increasingly what you're going to see is in the design process, architects and engineers, they're going to be using not just the historical weather data to model their buildings to inform their design. They're actually going to start using forward-looking weather data.
Oh, wow. I feel as though that has not traditionally happened. Right?
Not widespread for sure. Okay. It's happening in some circles, but it's going to start happening much more frequently.
Interesting.
And so those models exist that they take, all the historical weather data, they take all the, various climate models that exist out there, and they actually will forecast the weather over the next, 20, 30, 40, 50 years. And so designers will start using that data to inform their building design. So not just how much insulation do we need to meet the current code and their current weather, but how much insulation will we need 50 years from now when the temperatures might be X degrees warmer?
Right.
What do we need to do then to make our buildings more resilient, more future-proofed? And so I think that is a trend that is just now getting started, and I think will become more more prolific and maybe even adopted by code at some point. I don't know, but I think that's a possibility.
We'll see. I think that's certainly a fair assessment as we see things change more rapidly than we ever have before in our environments, and then obviously in order to keep up our structures, in order to keep up with the changing environment that we experience on a daily basis.
Yeah, exactly.
That is exciting. Galen, that is all we have today. I really appreciate you sitting down with us, coming all the way over from Colorado. It's been an absolute pleasure.
It's been good to talk to you, Christian.
Thank you for joining us on Building Science Digest. Thank you all who watched and listened. Please follow and like, and then listen anywhere you can get your podcasts. Thanks.
Thank you.